Welcome to the course on FPGA based signal processing systems. As we are learning this finite state machines, we'll also look at the counters as the finite state machines. So before getting into it, a few more functions which needs to be known here. So when we are writing the test bench, we would be giving the stimulus to test the Verilog module. And the stimulus can be, for example, in the previous lecture we had the dollar random. So the sequence input was random one, and we would like to store that information of sequence, what input had been given to the module, or what is the output of the module, the found, where are the founds have been, and where are the sreg, how it was moving. So we can get that file in the Verilog module, from the Verilog module, that is the using one function as $dump file. So dump file, which gives this VCD, specify the file name as the VCD file. And how do we use this in the statements? As a statement, $dump file, give the file name. So sequence.vcd, or any other name of your choice, that it could be input.vcd, and so on. So the other task which can be as can be learned as $dump vars. So dump vars dump all variables. So all variables, simply if you use $dump vars, it dumps all the variables in the module in a file. Okay, so the dump vars can also be which can be used with store particular variable also. So we can say, suppose dump vars $dump vars levels, levels list of modules or variables. That means the level can be 0 or 1. Okay, if we say, suppose write this is 0, okay, the dump vars 0, store variables in the modules of all the sub modules also. So it would take the given module variables and the modules which has been given as sub modules or instantiated ones. If this is given as 1, it just takes the variables of the top module. Okay, it doesn't care about the sub modules. Okay, so the levels can be specified. What are the variables we need to store can be specified directly also, that dump vars within the bracket you can say the variables with levels. Okay, so list of modules or variables can be specified in this within the dump vars. So there are dump file, that file itself will be created in .vcd, and you give the file name, or dump variables, which is used to store the variables with levels. The sub modules are required or not. If sub modules are required, then go for 0. If it doesn't, then put that level as 1. So this is if it should be noted, we'll store all variables in the VCD if specific list is not given. So if you use simply $dump vars, it would be just storing all variables. And another one is $dump on. So whereas it starts with the storing of storing process. For example, that is the time at which it is given. So your simulation is going from suppose 0 time t equal to 0 to 100 nanoseconds. So you want to store the variable of last 50 nanoseconds. So then you can give a $dump on, that is 50. The syntax here is the hash time, that is the hash 50 starts dump on. So it will start dumping on the variables or storing the variables from 50 nanoseconds. $dump off in this, stop dumping the variables, I mean storing the variables. It stops them. That the syntax is again hash tag, and time, it can be of 100. So at $dump off, hash 50 to 100, store the variables. So you have the control over it instead of dumping all the variables, which is unnecessary. If it's required, yes, you can do it. Otherwise, you can take the specific variable and start storing it for a specific time, is to save the storage space. So let's use this in the sequence detector example we had done. 100 module sequence detect TB. In the test bench, I just give that. I am not giving the module code here, and it is available in the previous lecture. So reg clock reset and the sequence. output wire is found, and instantiate that module what we had in the Verilog module for the sequence detector of 100, and this particular diagram which is having the state memory, next state logic, and the output logic. After this initialize this after initializing the Verilog module, initialize the inputs. It is mandatory to have this initialization, clock 0, reset 0, and sequence 0. Then hash reset 1, you can make it reset 1 or reset 0. So this is the pattern which we had been using in the previous example as well. Hash 50 reset 1, sequence is 1, and then reset made 0, sequence is 0. To detect this anyway, we monitor this all the variables as usual, that is $time. This is clock reset, sequence, and found. End always hash 5 clock equal to not clock, and then always begin use the sequence as $random. That is we had also used in the previous test bench, that is generating ones and zeros in a random fashion. End, and then go to the dump file. So here's the example for the dump file, sequence dump.vcd. So put it in the quote. Okay, so this would create here a file .vcd file in your folder where you are in the project folder, and then dump where's 1, sequence, and found. So in this variable, that the top module, sequence and found are the variables. So we given this 1, sequence, and found. So it can store that value in the .vcd. If you open the .vcd file and you can find that with respect to the time, it could give this. Here again, this given as hash 100 $dump on. So hash 100 onwards start dumping these variables. Okay, so we have given the specific time to this, and then hash tag 1000 dump off. So after the 1000, do not store those values. That's what the instruction says, the dump with them, and then end. So these 4 can be used in the test bench for saving those variables. So for future use, or you want to take the data and use it in some other file, some other module as a read, or in the real time we need to analyze those. So we can have this type of files, .vcd files, and then the variables which needs to be stored can also be defined here, and what time if you want to start the dumping process or saving the variables, or where it should be stopped. So those things can be mentioned in the test bench itself. So this is going to be a separate initial, begin, and end syntax, which because begin end we use because of the multiple statements over here. So this is separately along with apart from the $monitor and then dollar display, also the stimulus and the initialization. Along after this, you can put, after generating the clock also, you can put this variable which needs to be stored. Okay, so this is the sequence which is generated using the random $random task here, and the found 100, you can see over in many places that wherever there is 100, that gives the found equal to 1. Other places it is 0. And this is the sequence of the log file which is detecting 100. Okay, 100 here, 100, so on. After that, so the continuation of this 100 could also be seen over here. So you have not shown the particular stored file. Okay, you can always take out the .vcd file and see that what from time it is generated and stopped. The instances can be found in the .vcd file, and what are the variables, and if you have the submodules, give them also in the level as 0, so that it would save the submodule variables as well. So coming to the next example for the FSM, that's a counter, which is a switch tail counter, or the you must have seen the simple ring counter, and this is Johnson counter, wherein the last bit of the counter is getting complemented and shift to the first place. Okay, so this counter, how do we get the how do we make this in the Verilog, or how do you make the Verilog module for this Johnson counter? Okay, so the counter, which is 4-bit here, considered 4-bit. So each of this has some used states, and these ring counters especially, this is a switch tail. So the last bit is complemented and shifted to the first bit in the ring counter. Suppose this is 000, and the last bit is complemented and then put over here. So that is 1, and then this is shifted, so 1000. So this last bit is 1, you can see over here, and then this bit is shifted. Okay, so that is the logic for the switch tail or the Johnson counter. So where if you can use the D flip-flop, and we'll see the digital circuit or equivalent digital circuit of this as well. So this type of counters will not have all the states used in the use. Suppose we start from 000, this next state is 100, you can see over here, and then again this gets complemented. Okay, so put it 1, and this 100 is moved to here, so you get the next state as 1100. So the next state is where 100. Okay, so next one, it becomes 0, become 1, and then 110. So you get this similarly at this point, and then make this 1 and then 111. So this is the next state. And if you complement this again 0, this will be 1011. So that is the next state. And the next state would be 0, and then you copy this 011 here. This is so third bit is the logic which we can say, that is the third bit is 0 to 3. If you suppose consider this as a register with 0 to 3, so this would be always that the complement of this, they name these variables and complement the first bit and put it at the third bit, and then shift this 3 to 1 in the next two. So you can have the statement which has this 3 bits over here, and then this is complemented bit over here. So you can have the concatenation operation in which the first bit is complemented, and then these 3 bits are given in the concatenation operator. So that is a simple logic which can be used to model the Johnson counter. That is one. As a state machine, let us look at this as a state machine. How do we generate the Verilog module for this? So here 0 1 1, the next state is again, so 1 is made to 0, and the 3 bits of it is getting over here. So finally 1 is complemented here, and the last 3 bits are given over here. Okay, so now this is the state which is using. So if we consider this 4-bit, then there are some states missing because of the 16 combinations of 4 bits are not all of them available in this case. So what should we do if these states are part of the counting sequence or not? Okay, so supposing it is 0 0 1 0, it's missing over here. This is okay, the missed states are given over here. So the 0 0 1 0, then again complement this first bit and move this 0 0 1 here. Yes, it can if this is 2, then yes, it is going to 9. Okay, so now again it is going to here as a another state. So this is complemented, and then put this. Yes, these are again forming a some sequence in this counter. The states are, but these are not used in the main when it starts from 0 0 0. Okay, so these are called the unused state. Suppose a counter or the input given to this counter somehow is in any one of this, then it would be moving here only. So or if you start the counter from 0 0 0 0 only, it would stuck. It moves in this with respect to the clock edge in this states only, in these states. So if there is any of this input which is of the states from here, this unused states unused, then maybe from 9 it is brought to 0 0. It can be from anywhere, from 0 to 0 0 1 0 also can be brought to this and follow the main path. Okay. So are the counting sequence which are used normally. So that's the idea. So this is also called the self correction. So if there is any input of 0 1 0 0 given, then bring it to 0 0 0, or anywhere in this state bring it to this state. Need not be, don't go here. If the input is here, the correction is done at 9 state number, this known as 9, and then bring it to 0 0 and go over the state. Okay, so if any of this instead of going to 9, okay, so this one, so 9, so don't go to the 0 1 0 0. So if it is 0 1 0 0, yes, it would if you give this input, then it follows this path and then come to 9 and go back to the state. Okay, so that is possible. So the unused states are corrected like that, to make it self correcting. So to make this self correcting, use any one of these unused states and make this unused states next state as the used state, okay, in the design, so that this counter logic will not stuck over here. Suppose 9 is given, that counter should not be stuck at that point. It should move to the state where those are used states generally. So the correction has been done in this case. So when instead of going to the next state as here and go to the 1001 as 000. So let's see the example of the design. So the present state, all of them, this is x, y, z and t. So we used q0, q1, q2, q3 in the previous designs. That is same notations also can be followed. So q0 star, q1 star, q2 star, q3 star. So the star is given as used in the next state as well. So 000, the used states are listed over here. The 000, the next state is, this becomes 1 and the 3 bits are pushed over here. Okay. So similarly, this is complemented, and then 100 is pushed here in the next state. So it moves on up to this point, it is fine. So 001, so it becomes 0 and all the zeros here. So it ends over here. It started from 0 0 and then end over to end to 0 0. But what happened to the unused states? So list any one of the unused states. 0010, yes, it can go to the this is complemented, and then 001 is copied over here. Fine, it goes to 9, and then after 9 you may have to, otherwise it will be going through that unused states only. Okay, so we have to bring it to the used states. So 1001 is again now changed to 000. You see the mark which we had done is so the next state is assigned. You are forcing this to the counting sequence to bring it to the 000. So 000, and then it would follow that this pattern what we have given, that is 4. Also the case of 1010, that is also another unused states here. 1101, it moves to 1101 here, so which is given. So here, okay, this is here, and then it moves across this. Only this part is the 9 is corrected. So this is unused state, to mention this is an unused state, but 9 is now changed to 000. That should be noted here. After that, all the states are listed over here. For if you bring this 9 to 00, then the next state is 4, then 0100, and then 1010 for that, from the unused state that we all is listed over here. And if you notice, some of them ABCD also has been written. We just given this ABCD, and that the thing is naming this for a Verilog module, we consider this as current states. So the current states are named as A, B, C, D, E, F, G, H, and so on. Okay, just naming them L, M, N, O, P. So this is named as L, state L, and this is state M, P, and we just avoided O, and took and then it is P, Q, 0101 Q. Okay, so the states are listed here, A, B, C, D up to Q except that O. And once you have the current states named, that will be defined as a parameter in the state machine. But for the digital design, that to get the digital equivalent of the state machine, so you need to have this Karnaugh map. So x, y, z, t, so a q0, q1, q2, q3, whose present states, what is the x, the next state. Okay, so that is q0 star here. So we have this force, all of these ones are picked up in the Karnaugh map here, and here, and put it for the x star 1 1. There are 1 2 3 4 5 6 7 8 8 of them. So it shows this 8 and minimize this variable as it comes out to be t dash. You can see that over here. Okay, so it's t dash combining this 8. And the other for y, similarly q1 star, this is xy, this is one term, and then the other one also xz, this is from this 4 variable. Okay, and x, so again one is from here and here. The third variable is getting, we are getting x t dash, third term. So q1 star are the y output, gives the xy, xz, and xt dash. So next one, next state here from the table, this one, if you picked up 1 2 3 4 5 6 7 8 of them again, so it forms 8 minterms here, is equal to y, it simply gives y. And the next one again, with from the table we get 1 2 3 4 5 6 7 8 of 1 for t, so the t dash is z. Simply this is going to be z. So we get these variables. It is now easy to get from these variables. You can have put star t plus, so this is same as x of t plus 1 z of t plus 1. So we have this 4 flip-flops over here, for the 4 bits specified, and each y star especially, it gets d2 as this xy, xz, and xt dash. Okay, so and coming and adding all of them to give to d2, that is going to be the, because d flip flop will take this as next state. So here d1 is given y, y. Okay, so this is going to be simply y, and here t is giving to z, z, this is z, and q1 dash is getting into d3. Okay, so the t, the xyz can be, so this is the equivalent digital circuit. So we can use the d flip flop modules what we had already made, instantiate them 4 times, and then instantiate these AND gates and OR gate and connect these. Always block is already in the D flip flop is made always block. So instantiate these D flip flops and assign statements for this would make this Verilog module of the in that version. So this is the digital equivalent of this counter, which is having the used and unused state. So we made it self-correcting. So if they test at any of the 0010, then 2 or any of the unused state, and it will move on to, if there is a next state, it will move on in that unused state and then go to the final state of 9, and we brought that 9 to 00. That correction has been done, so it brings to the used state. So self correction has this to be done in that way. So the clock which is given for the all of the flip flops needs to be noted. This is synchronous counter design. So from this we would take this example for Verilog module, making that module Johnson counter, clock, reset, and you see there is an input given. So I'll explain that input, what is the reason for this input, just to load some value to test it with unused state. So here is output sreg and snext. It is given here reg and snext, sreg and snext. From this, the parameters, all the current states, we have named it here in the table ABCD. If you see them, if you see here in the table ABCDEFGH, all of them are listed, are defined in the parameter. To make it as a synchronous sequential detector, or the as in the case similar to that fashion, or FSM, for 0 to 3. So A is 4 bits, again this B is 4 bit 100, So all the states are defined. Okay, so except O, it will be A to Q. You have this, all of them, N, P, Q. All parameters are defined. That is called all the states, used as well as unused states. Okay. So from this, if you may wonder, if reset input is assigned to SREG, so the current state we are taking as an input through a signal. It can be of any signal, it can be an input signal, or enable, through enable we can have this input to be assigned to the current state. So here it is done with reset. It can be this can be a enable input. Then else I'll assign this next state to current state. So that is the state memory what we created. So the state memory gives that here, this one. Okay, if reset, go to the SREG in the else. Okay, so then if reset is this, then assign it, or SREG equal to S next. Okay, so here the state memory ends over here, and then next state logic. The next state logic will always at the rate SREG. Okay, begin in the case SREG, which is to test the current state, and then where it is moving. So from the state machine we have the if it is at A, next state is B. If it is B and next state is C and next state is D. Just we have to list out those where this next states are. Next state is H. Okay, the continuously 16 states are defined. It includes that 9 state which is going to 0 0 A. Okay, so J, after J, it is at J it is going to A. You can notice this is bringing the correction which is done over there. Next default is A, in case, and then end. Okay, so this completes the next state logic. Okay, so what we had learned from the state machine, that how to make the next state logic. Begin, end. So then now is this because there is no output logic in this case. You should note down that in the state machine it doesn't have this output logic to have this, whether this count sequence, like in the sequence detector, the found has been indicating that what is the sequence is detected or not. If it is 1, then sequence is detected. Here it's nothing like detecting a sequence, so it is just moving around. The states are moving around, and it coming back to the 0 0. Okay, so there is no output logic is given in the code. The code doesn't have this output logic because of the no such output logic exists in this particular counter examples. So module test bench, just input reg clock reset, and the input here, input is that what we had, if either you give 0 0 used states, or you can bring the counter give the input to the counter to any of the unused states, so that the enable signal or the reset one which is used in here, we have used the reset, which could be enable, to load it in the register, and then keep moving that from the next SREG, from SREG. So the outputs wire SREG, and then wire next. So current state and the next state. Then the next instantiate that module Johnson, that reset SREG and S next. Initial begin clock reset is 1. Okay, so input is, so you can see the stimulus here. So it's 0 0 0 0 is assigned to input. For this reset, meaning that we have the, it is not we have to start with the 0 0 0 used states. If reset is 0, then it will move around that used states. That is hash 30 given over here, hash 400. Again, after some time, through the reset we get this input, store the input as getting this input and store it to move it in the counter output, that is from 0 1 0 0. Suppose that's one of the unused states, and then reset is 0 hash 50. Okay, so this is end. Always hash 20 is clock is not equal to not clock. So stimulus, initial, begin, display them SREG and S next, which is needs to be this is to just have the I just make this as enable to get either the 000 any input to the counter. Okay, to store it in the current state and then start moving it from that state, the end, and then end module. So here is the output which can be seen, the clock edges. Here the clock edges are, and through reset, okay, you can see that reset is 1 and the input is given 00. Okay, so the input, once this during this signal what we get and store it in the current state. Okay, so the current state is 00. Now from here, whenever this has become 0, that this is moved to the 0000 current state, and then from current state every clock edge you can see that next states of the next state. This is 100, that is complemented, and the last 3 bits are copied over to the first 3 bits, and similarly 1100, 1110, 411. So here goes up to this one, goes up to this, it is coming back to here 000. Also again it starts to 1000. Okay, here the second one. Okay, after this some time, next clock edge it is made, that again through reset getting the input. Okay, some that is maybe any signal which allows to store the value from which it should be started in the counter. That is 0100 is the value which is given to this, and it gets next clock edge. You can see this is 1100. So here it is stored. This one is stored from this clock edge, and after that these are the unused states. Okay, 1001. So you can see the self correction which is happening. It goes to the 000 and bringing this counting sequence to the used states 100, 1100, 1110, 111. Okay. So the X next is that actually it needs to be copied. The X next is need not be known. Actually, you can see them that X next is copying to the SRIDGE. Okay, so that is the way why it is plotted over here. So you can see. So the only thing to be noticed here is this, that 9, and you can also load this values of unused states from which it should be started, and the correction, self correction is done in this case. So you have this SRIDGE in the printed ones in the log 000 going to here up to 0 and moves in that state only. And after this we have loaded the value 0100, from which it goes up to 9, and then at 9 you can see the self correction 00 bringing it here, and then following the used states. So this is the example of the Johnson counter, switch tail ring counter, switch tail counter. In this ring counter, you will be just copying the 4th bit to the first place and then shift the first 3 to the first 3 with the last 3 bits of this. So here in that case, suppose this 1 would be this. Okay, so in case of ring counter, so it will just move here and then move. So 0 1 0 0, that will be ring. So if the first bit is complemented in the Johnson counter, as I explained there. So the switch tail counters also will have some used states and some unused states. If you want to design this in the ring counter, simply the ring counter will have some used states and some unused states. So you have to define this unused states. What is the next state for this unused state? One of this, to bring it to the regular used states, so that the self correction can be done in this type of counters, and look at them as a state machines. So we have given the states defined with A, B, C, D and all, and so equivalent circuit also, digital circuit is also can be, it also can be done. That is what is I have shown the example of how to make this digital circuit, so that could also be used to develop the Verilog module for it. The flip-flops and the combinational logic, state memory and the combination logic combination can be with the in the module, Verilog module. So ring counters and the Johnson counter is part of the ring counter. Okay, so mainly counters can be looked into as state machines. Okay, especially it can be more state machine because there is no output logic here. This current state is going to be the output, and the input is not going to reflect on the output. Okay, so it can be designed in the fashion of more. Even this type of counters, again, suppose we have this mod counter, mod 2 or mod 4 counter. Let's take for an example 00011011 state. Can be, it's moving from one to another during the every clock pulse. But if the input is 1, move to the next state. Okay, so if input is 0, go back to the previous state. Input is 0. So that way this can be made up and down counter as well. So the design can be made as an up and down counter. Our only up counter is required. So from 0001, if 1 is received, go to the next, otherwise stay in this place only. So we can use this only for up counting, but not using any of the others. Stay in that state. If 0 is received, stay in that state. So this is also one model of the counter which can be designed with this FSM, and this is another one which up and down counter can be designed with the FSM, whereas you need inputs 1 and 0 here. So okay, in the design. So equivalent digital circuits can also be obtained. So looking at the finite state machines of the Mealy Moore and then with the counter as well as sequence detectors are part of the FSM. So with this we would like to complete this finite state machines. Thank you.